Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 8 from the May-June 2023 Cambridge Paper 1 Variant 2 Pure Mathematics paper from the 9709 syllabus. This is Paper 1 Variant 2. Question number 8 here is about this graph. It says the diagram shows a graph of y equals f of x where the function f is defined by f of x equals 3 plus sine of 2¼ x for 0, x is between 0 and 2 pi. Okay, so I know about this curve a few things. One of the things I know it passes through the y-axis. If it passes through the y-axis, we can see that's going to be where at 0, 3. That point is 3, just before pi. We know pi is 3.142, so this is just above 3. They've given these in terms of pi in the y and the x-axis, which is a bit not that common, but anyway, this would be the point 3, 0, 3. This would be the point 0, 3. And this point here, 2 pi, and, well, we could work out what it is, I guess. We could find out what happens when f of x equals 2 pi, but I'm just going to call it 2 pi and b. We don't really need to know the coordinates, so I'll call this 2 pi and b. So this is the point 2 pi and b. All right, so I know on the original function f of x, we have the point 0, 3, and we have another point 2 pi and b. And in the inverse function, f to the power minus 1x, the inverse function, we know that the x and y coordinates, they are switched over. All right, the inverse function, 0, 3 will become 3, 0. And whatever b is, and 2 pi and b will become b and 2 pi. So we know that this is going to go through 0, 3, that's going to now go through 3, 0. So 3, 0, remember 3 is just before pi, 0 is going to be somewhere over here. It's like that same distance between there, and they're the same scale, these two axes. So it's going to go to this point here, which this is 3, 0. And it's also going to go through the point b, 2 pi. Now, b is somewhere just after 3 pi over 2. So it's going to be somewhere just after 3 pi over 2. And it's going to be 2 pi on the y. It's going to be up to here. So it's going to be somewhere over here. That's going to be the point b, whatever b is, and 2 pi. As I said, we don't really need to work out what b is. So I've just called it b because we can locate where it is on the graph easily. So now we know that the inverse function is going to pass through these 2 points. The other thing we know is that if we compare f of x and f inverse of x, I almost wrote dash. Dash doesn't mean inverse. Be careful of that. Dash means the first differential, but we're finding the inverse here. Okay, if we compare these two, then we can say that to get from there to there, you have to reflect in the line y equals x. Okay, so the inverse function and the original functions are reflections of each other in y equals x, because as we can see, the y values become the x values become the y values. So what we do is we can draw a line here that will make it easy for us to actually figure out what's going to go on. So I'm going to draw a line, y equals x. Now y equals x is a line where the x and y coordinates will be the same everywhere. So 0, 0, half a half, pi, pi, and so on. So they're going to go through the same value of x as they do of y. So that would be the line y equals x. So we have to reflect this line, this curve in this line. So we can just draw our line. Of course, you're going to do it with a pencil in the real exam. So you must do this in a pencil. So they're going to intersect at this point as well. They always intersect on the line y equals x. Okay, so it's going to look something like this. Try and do it as neat as possible. It's going to look something like this. Right? Something like that. Okay. I haven't done it too well, but that's fine. Okay, that's okay. I'll just do it one more time to make it a bit more perfect, if I can. So it goes through this point here, and this point there, and through there. So over here, it's going to be like almost vertical. It's like almost, it's almost horizontal to start, coming almost vertically down. It's like the top of it's turning, and then it's going to go something like this. Not bad. That should suffice. Okay, just get rid of these double line things. Okay, I think that should be fine. Okay, so here we have the graph of y equals the inverse of fx. Reflection in the line y equals x. The x coordinates and y coordinates swap over. So it says here on the diagram, sketch the graph. That should be fine for your graph. You don't really have to put any of these points. I put them there just for our understanding and our reference. Now it says find an expression for the inverse function. Find an expression for the inverse function of f. So what I'm going to do now, I'm going to take our original function, f of x equals 3 plus 2 sine of a quarter x. All right, and I want to find the expression for the inverse function. They're not telling us to find the inverse function. They're not telling us to write down the domain of the inverse function. They're only telling us to write down an expression for it. If they said find the inverse function, we would then normally have to write down the range of it as well. Okay, so the domain of it as well. It's not too difficult, but that's something you have to care. If there's find an expression, they only want the algebraic expression. If they said find the inverse function and the original function has some restriction in the domain, then you should write down the domain of the inverse function as well. Okay, but anyway, here, well, first step is I'm going to call f of x y. So 3 plus 2 times the sine of a quarter x. Now, the second step I always like to do at this stage is to write y as x and to write x as y. So 2 times sine of 1/4 y. And now I'm going to make y the subject. In the process of making y the subject, we will then have got the inverse function. So first of all, let's isolate the y term. Let's subtract 3 from both sides. So we have 2 times sine of a quarter y. And then we can divide both sides by 2. So you end up with sine of a quarter y is equal to x minus 3 over 2. Then we can take the inverse sine of both sides. So I'll write this on this side. The inverse sine of a quarter y will leave us with a quarter y. It's like they cancel out. And you'll have the inverse sine here of x minus 3 over 2. And then we multiply by 4. So y equals 4 times the inverse sine of x minus 3 over 2. That would be the inverse function. So we can write this as f minus 1x equals 4 times the sine of the inverse sine, of x minus 3 over 2. And that's the answer to part B of this question. That would be the graph of this function. And we can see that its domain would be between the values of 3 and whatever value this is. The same as the domain of this, as the range of this function. The range of this function between these values is between these 2 points here. Okay, and the domain of this would be between these 2 points here. And if we wanted to work out the actual domain, we would work out what the value of this is when y is equal to 0. So we'd have, that would equal sine of a quarter x is equal to, it's going to be a half. It's going to be minus, if you subtract 3 from both sides, you have negative 3 equals 2 sine of a quarter x. So you'll have minus 3 over 2. Hold on, minus 3 over 2. Is that right? And f of x equals, sorry. Yeah, no, when we will find, if we're finding this point here, if we're finding this point here, we're going to put x equals 0. So you'll have 3 plus 2 sine of a quarter. Okay, we know that point. If we were trying to find this point here, we would put, excuse me for that. If we were trying to find this point here, we would put x as 2 pi. If we're trying to find the y value of this point, we would put x as 2 pi. So you have, you would end up with 2 pi. You'll have 3 plus 2 times sine of a quarter times 2 pi. That will tell you the y value of this point. that will be what the y value of this point is, which is 3 plus 2 times the sine of pi over 2, which is 1. So that's 3 plus 2, that will be 5. So this value here would be 5, okay, which is just more than 3 pi over 2. As we can see, 3 times pi divided by 2. So it's just slightly more than 4.71. That's right. So that would be 5. So this would therefore be the range of our function would be between 3 and the domain of our inverse function would be between 3 and 5. Okay, but here we're not asked to find that, so we're fine. Okay, sorry about the little jumble there. But basically what I'm trying to say here is if the question had said find the inverse function and it didn't say an expression for the inverse function, then it means you should give the domain of the inverse function. In this case, we don't have to, but it's possible that they could ask you and you would have to. In that case, you would have to find what the range of the original function was. And as we just calculated, this is 3 and this is 5, the highest it reaches. Okay, so because it's equal signs, okay, it's going to go between these two values here. So the domain of the original function, of the inverse function, would be the range of the original function. The range of the original function is between 3 and 5, the y values. Okay, so the domain of this function, you'd say x is between 3 and 5. That's the domain, and the range of this function, the range of the inverse function, would be the same as the domain of the original function. As we can see, it's between 0 and 2 pi. Okay, the range of the inverse is the same as the domain of the original, between 0 and 2 pi. Okay, so these are extras here we don't really need to know for this question. But it is possible that they might ask you those questions in an exam question. So you have to understand what to do. So the fact it says find an expression for means you don't have to write the domain of the inverse function. If it just said find, okay, the inverse of f of x, find the inverse function, then you must state the domain of this inverse function, which will be the same as the range of the original function. Okay, so that's very important for you to understand in this question. Now for part C. It says here, the diagram above shows part of the graph of the function g of x equals 3 plus sine a quarter x for minus pi, 2 pi to 2 pi. Okay, so it's shown a part of it. It hasn't shown the whole of it. Complete the sketch of the graph of g of x on the diagram above and hence explain whether the function g has an inverse. All right, so this now we have to go all the way back to negative 2 pi. So to be sure, what we could do is we could, plot some values in here and see what happens. I personally think it's going to just be it's going to be like, as we know, the sine curve goes like this. Okay, it goes like, the sine curve and the cosine curve goes like this. So it's going to be like something between here and here. So that those values will be kind of replicated. But let's see what happens. Let's actually put some values in. So we have g of x equals 3 plus the sine, 2 sine, of a quarter x. So we can say, let's see what happens when we put x equals, let's go to minus 2 pi. Okay, so let's find when x is minus 2 pi, you're going to have 3 plus 2 times the sine of, you're going to have minus 2 pi times a quarter. That's going to be minus pi over 2. And the sine of minus pi over 2 is minus 1. So you have 3 minus 2, which is 1. So it's going to, minus 2 pi is going to go to 1. Okay. Now 1 is going to be somewhere around this region here. Let's see. So a half of pi is 3.142. So let's say pi divided by 2 gives us 1.57. Okay, so that's going to be 1.57. So it's going to be below this. Okay, so it's going to be somewhere over here. Okay, it's going to be somewhere over here. I'm guessing that same distance there will be the same distance there. Okay, and when you've got minus pi, like here when you had pi, it's between these two here. Okay, I'm guessing it's going to be the same. All right, I don't think it's basically, you can see it's going to be the same. It's going to go exactly the same as this. Let me just do it a bit better. It's going to go through here. It's going to meet up with that like this. Something like that. Let me make it a bit more curved here. It's trying to be a bit more accurate. So it's going to kind of go down. And then that's going to be like the maximum point that it reaches. Something like this. Okay. Try to do my best. So that's going to be the completion of the graph. All right. So there's the sketch, and hence explain whether the function g has an inverse. Well, a function has an inverse if its gradient is always either increasing the whole time or decreasing the whole time. Okay. If it's increasing and decreasing, all right, or decreasing and increasing, if it has a turning point in it, okay, in that section, then it won't have an inverse. This one is always increasing, as you can see, up to these 2 points. If I continue drawing it on this side and this side, okay, then it won't have an inverse. Then it will be something which is going to be a many-to-one function. But this is a one-to-one function, okay, as it's only increasing. So we can say it has an inverse. So it says, explain whether the function g has an inverse. You say g of x has an inverse because for the domain it is defined for, it is always increasing. Okay, or you can say it is 1-to-1. Okay, so it has an inverse because it's a one-to-one function for the domain for which it is defined. Okay, so there's the answer to part C. So we don't have to actually, it's only worth 2 marks. We don't have to actually work out any values. We can just understand from our understanding of the sine curve that it's going to basically do this, right? Because the sine curve has this pattern where, you know, it goes like this and like that and like this and so on. And this is just like a transformation of the sine curve. So it's like you've got this part of the curve, okay? And we just basically, it's like we've got this part of the curve here drawn. Okay, that's what the part was drawn. And this is the next part that we have to just continue. That's basically what we can just do. We don't actually have to work out any values here. It's only worth 1 mark. And the second part of it is for stating that it's a one-to-one function, so it has an inverse. Excuse my bad handwriting. Then it says, describe fully a sequence of 3 transformations. 3 transformations which can be combined to transform the graph of y equals sine x for x between 0 and x between 0 and a half pi to the graph of y equals f of x. Okay, so y equals sine x between 0 and a half pi until y equals f of x, which is the graph that we had between 0 and 2 pi, which is this part, the graph that we had before, which was the one in black. The y equals f of x was the graph we had in the first part, which starts from 0 up to 2 pi. Okay, so how does that transform? How does y equals sine x transform to this? Well, we can look at y equals f of x and see what's happened. Okay, so we know that f of x, we have, this is 3 plus 2 sine of a quarter x. So the first thing we always start with is the transformations inside the function, the horizontal transformations. And here we have something like this. Let's call it h a quarter x, which is basically where you have a horizontal stretch. Okay, and it has a factor of, now the factor is always the reciprocal of the number that's being multiplied inside the bracket. So it's a factor of 4. The reciprocal of a quarter is 4. So first is a horizontal stretch of factor 4. And then we go outside the function. We're going outside the function. The other transformations are not inside this bracket. They're multiplying the whole function. It's like 2 times, and we start in the order of BIDMAS. So we start with the multiplication. So it's 2 times the sine of a quarter x. So it's 2 times the function. So when you multiply the whole function by a number, okay, it becomes a vertical stretch. And outside the function, things act normally. On the y, they act normally. So it's going to be a factor, in this case, of 2. All right. Okay, and then the third transformation is the 3 that's added to it. It's like you're adding 3 to the whole thing. 3 plus is adding 3 to the whole thing. Now that becomes a vertical translation. Vertical translation, which we're going to describe using a vector, which is going to be, go 0 across and 3 up. Okay, it's a vertical translation of 3 units. So when it's outside the function, when it's the y coordinates are affected, it's normal, you put plus 3. If it was inside, for example, if it was h of x minus 3, okay, then you would put outside here, you would put, or if it was plus 3, you put minus 3 on the vector. You put minus 3, 0. When it's inside, it's the opposite. When it's outside, it's normal. When it's a stretch, when it's inside, you write the reciprocal of the number multiplying. The reciprocal of this factor will be the stretch factor. When it's outside, it's the same factor that's multiplying the whole function, which is the stretch factor. Okay, so that's describing those fully. Horizontal stretch factor 4, vertical stretch factor 2, vertical translation 0.3. So 1 mark for the description of the transformation, and 1 mark for the detail of the transformation in terms of the stretch factor and the vector that takes you, okay, or that describes the translation. And that's part D done, and I think that's the end of the question. Yes, it is. So that concludes question number 8 from this paper 1-2, May, June 2023. Other questions from this particular paper can be found in the playlist that will appear in this section here at the end of the video. This section you will find a link to the playlist that takes you to my questions dealing with trig graphs from P1 of Cambridge, and I will give you also a link here to my work on transformations from P1 of Cambridge, and I'll link you here to my work on transformations of trig, or transformations from P1 of Edexcel, because there's a lot of more questions in there and you'll be able to see that. Thank you for watching, and see you soon.